So hi, good morning all. So I'm a postdoc at UCSC, mainly working on scales data reduction pipeline. But today I'll be talking on the some interesting results from the examoon candidate WAS49B. So the real advantage of ground-based observation are the possibility of using high spectral resolution limited by photon noise rather than photometric stability. So this spectroscopic observation will help to resolve, detect, and characterize individual atomic and molecular species without using atmospheric retrieval models. So the figure is a time series of high-resolution spectroscopic observation from espresso. Yeah, so we all know so when planet transit, part of the light coming from the star will passes through the exoplanet atmosphere before it reaches the observer. So that extra absorption is what we are looking for. Along with that, it is expected to have a blue to red shift as the planet moves from ingress to egress. This velocity and the strength of the signal both are equally important to understand the origin of the absorber. So today I'll be particularly talking about sodium doublet at 589 nanometer. And sodium is considered to be the most commonly detected element in the atmosphere of hot Jupiters and Saturns, especially mainly because of its large scattering cross-section. And this figure is the sodium D line from KPF of WAS49B. And the vertical lines are the expected rest frame of the lines. The sodium can also be coming exogenic to the system, which means it's not coming from the planet atmosphere, it's coming somewhere outside of the planet. Similar to our Jupiter Io system, where the tidal interaction between the Jupiter and Io make volcanic activity in Io, and which will produce particles like sodium, potassium, sulfur dioxide, carbon dioxide. And this particle will follow the orbit of Io around the Jupiter. So that's what shown in the figure on right side, where you can see if you observe the Jupiter as a point source, we can see a cloud of sodium orbiting around Jupiter. So it's extending up to 1,000 Jupiter radii in some times. And in the left side, the figure is like the Juno-Geronimo image of Io at 5 micrometer, where you can see the volcanic activity happening. So this work actually started when Wittenberg detected sodium in the atmosphere of WAS49B in 2017 using 3 HARPS observation. And what he noticed, like a very strong sodium signal. The sodium was observed to extend up to 1.5 times the planet radius to reproduce the observed transit depth, which is 3 times the sodium altitude probed at any planetary system to date. And if we think that the sodium is coming from the atmosphere of the planet itself, if you want to reproduce the observed transit depth, the atmosphere should have a supersolar sodium abundance, at least 5,000 times the solar sodium abundance, or a superheated atmospheric layer. Both are very unlikely to happen in the case of this particular system. And at the same time, Oza et al. Kind of tried to fit an XOIO model to the data, and he proved that the data fit well with the XOIO model compared to a hydrostatic or quasi-hydrostatic atmospheric models. And based on that, he listed a set of targets which potentially can host exomoon. So there we started, and the first priority one was WAS49B. So a little bit about the system. It's a G6 spectral type star with, and the planet is around 0.4 times Jupiter mass and with an equilibrium temperature of close to 1,400 Kelvin. So what we did, like we reanalyzed the 3 HARPS observation Wittenberg reported. Along with that, we had 1 VLT espresso observation, 1 Keck observation, and 2 KPF observation so far. So these are some observation details, and overall, like we had a pretty good number of exposures covering both in transit and out of transit, and good SNR. So this coming to the results. So these are the transmission spectra of the first 5 observation. The solid line is the best fit model to the data, and the vertical dashed line are the expected position of the line where when it is coming from the planet atmosphere. So overall, what we can see, it's like the strength of the signal, both D1 and D2, and the position, both are like varying from observation to observation. And in HARPS night 1, the signal strength was close to 0.8%, and there is no significant shift. And HARPS night 2, there is a very strong sodium signal, about 3.8%, and it was red shifted to close to 10 kilometer per second. And in HARPS night 3 and espresso, there is no significant detection and no shift as well. And in Keck Hires, what we could see is a blue shift of around 6 kilometer per second and a absorption signal which is comparable to HARPS 9.2. So Keck Hires, we know that it's a general purpose slit spectrograph, so we have to do an extra kind of wavelength calibration to achieve what we are looking for, and we could achieve around 300 meter per second velocity precision. So we also did like a narrowband light curve analysis by integrating the flux around the sodium D lines. So the white region in this figure is like where the transit event is happening. And in the Keck Hires, the blue region is a Hill sphere where the potential exomoon can gravitationally stable orbit. So the light curve is also like, looks like it's like very different from each other. The HARPS night 1, most of the sodium is coming close to ingress, and there is no sodium after the mid-transit. And the second night of HARPS observation, most of the it's a very strong sodium feature, and it's coming just before ingress. And in the third night, there is no detection at all. And in Hires, what we could see that most of the sodium signal is coming close to the mid-transit. And in espresso, there is less significant close to egress. Interestingly, if we check the duration of this sodium signal coming from Hires and HARPS night 2, it was close to 40 minutes, which means that the sodium was there 40 minutes and then disappeared. And so recently we have 2 kpf observation, but this is just a preliminary results. I have to work on the minimizing the systematic error on the data a little bit more, but still what we can see, it's like the D1 line is like we couldn't detect with a significant level, but D2 is looks like it's red shifted again close to 9 kilometer per second with a depth comparable to HARPS night 1. And the light curve was very much different from what we observed before, like the sodium was existed throughout the transit. And in night 2, again, it's a redshift around 11.5 kilometer per second, and it's a very strong sodium, which is comparable to the HARPS night 2 observation. So if we think that it's coming from the star because of stellar inhomogeneity, so it's as I said, it's a kind of a G6 spectral type star, and we analyze the center to limb variation and RM effect, which is not much contributing to the results. And then the second case, it's like whether it is coming from the planet atmosphere. As I said, even if we can, the strength of the signal can be explained using maybe like a past cometary impact on the atmosphere of the planet, or a superheated atmospheric layer, or a supersolar sodium abundance. But still the blue and red shift, what we are observing is quite difficult to explain. Even like the day to night wind circulation can be explained using a blue shift, but the red shift is not. So is it coming from a third body? So a natural satellite can explain the variable sodium in amplitude and position. And repeated 40-minute sodium signature observation in the light curve indicate the presence of an exomoon. The observed sodium evolution is similar to Jupiter Io system in our own solar system. And so where we are now, like, so we have 7 observations so far. So to fit the radial velocity curve of the exomoon. So considering a circular orbit, so we are roughly constrained the orbital period of 6 to 11 hours and a semi-major axis of 1.2 to 1.9 times the planet radius. Yeah, so conclusion is like dozens of more large aperture, precise, high resolution transmission spectroscopic observation are needed to build a radial velocity follow-up of the Doppler shift presented here. And along with that, it's not only the sodium, like the volcanic activities can give like sulfur dioxide, potassium, and carbon dioxide also. So if we have that complementary IR observation, that will be a great support to that observation. And so this is the best AI image I could make what I said now. So, but it's actually not correct because we don't know the cloud geometry yet. Yeah, I just randomly put like that. So, yeah. So it's an honor to use the Keck telescope. So I am sincerely grateful for the opportunity. And one quick look, I have a poster also today. So I'll be discussing on the data reduction pipeline for the upcoming instrument scales on Keck 2. Thank you.